Mastering reliability analysis methods. Reliability analysis methods are hiding in plain sight, waiting to be unleashed to revolutionize operational excellence. Where can one find a comprehensive overview of the various reliability analysis methods that support operational excellence? And how do these distinct approaches differ from one another in terms of their underlying principles, applications, and benefits in ensuring the dependability and performance of systems, processes, and equipment over time? Reliability analysis methods play a crucial role in achieving operational excellence by ensuring the dependability and performance of systems, processes, and equipment over time. There are various reliability analysis methods that support operational excellence, each with its underlying principles, applications, and benefits. Firstly, failure modes and effects analysis. FMEA is a systematic approach to identify possible failures in a system, process, or product, assess their impact, and prioritize them based on their risk. FMEA involves reviewing the functions of a system, identifying possible failure modes, evaluating their effects, and determining the likelihood of occurrence. This method helps to identify potential failures, prioritize resources, and implement corrective actions to mitigate risks. FMEA is widely used in various industries, including aerospace, automotive, and healthcare, to ensure the reliability of complex systems and processes. Another reliability analysis method is reliability-centered maintenance, RCM, which focuses on identifying and addressing the root causes of equipment failures. RCM involves a systematic approach to identify the functions of a system, identify possible failures, and develop maintenance strategies to mitigate them. RCM helps to optimize maintenance activities, reduce downtime, and increase asset availability. This method is widely used in industries such as oil and gas, power generation, and manufacturing to ensure the reliability of critical equipment. Root cause analysis, RCA, is a method used to identify the underlying causes of equipment failures or process deviations. RCA involves a systematic approach to gather data, identify possible causes, and evaluate their likelihood. This method helps to identify the underlying causes of failures, implement corrective actions, and prevent recurrence. RCA is widely used in various industries, including aerospace, automotive, and healthcare, to ensure the reliability of complex systems and processes. Weibull analysis is a statistical method used to analyze the reliability of systems and equipment. Weibull analysis involves fitting a Weibull distribution to failure data, estimating the shape and scale parameters, and evaluating the reliability of the system. This method helps to identify the underlying failure mechanisms, estimate the reliability of the system, and predict the likelihood of future failures. Weibull analysis is widely used in industries such as aerospace, automotive, and manufacturing to ensure the reliability of complex systems and equipment. Survival analysis is a statistical method used to analyze the reliability of systems and equipment. Survival analysis involves modeling the time to failure data, evaluating the survival probability, and identifying the underlying failure mechanisms. This method helps to estimate the reliability of the system, identify the factors that affect reliability, and predict the likelihood of future failures. Survival analysis is widely used in industries such as aerospace, automotive, and healthcare to ensure the reliability of complex systems and equipment. Monte Carlo simulation is a method used to analyze the reliability of complex systems and processes. Monte Carlo simulation involves simulating the behavior of a system, modeling the failure mechanisms, and evaluating the reliability of the system. This method helps to identify the underlying failure mechanisms, estimate the reliability of the system, and predict the likelihood of future failures. Monte Carlo simulation is widely used in industries such as aerospace, automotive, and manufacturing to ensure the reliability of complex systems and equipment. Lastly, reliability prediction is a method used to estimate the reliability of systems and equipment. Reliability prediction involves using failure data, such as failure rates and repair times, to estimate the reliability of the system. This method helps to identify the underlying failure mechanisms, estimate the reliability of the system, and predict the likelihood of future failures. Reliability prediction is widely used in industries such as aerospace, automotive, and manufacturing to ensure the reliability of complex systems and equipment. In conclusion, each reliability analysis method has its underlying principles, applications, and benefits in ensuring the dependability and performance of systems, processes, and equipment over time. FMEA helps to identify potential failures and prioritize resources. RCM optimizes maintenance activities. RCA identifies the underlying causes of failures. Weibull analysis estimates the reliability of systems. Survival analysis models time to failure data. Monte Carlo simulation simulates the behavior of complex systems, and reliability prediction estimates the reliability of systems. By understanding the differences between these methods, organizations can select the most suitable approach to achieve operational excellence and ensure the reliability of their systems, processes, and equipment. As I stood on the factory floor, surrounded by the hum of machinery and the chatter of workers, I couldn't help but think about the delicate dance of reliability. It's easy to get caught up in the daily rhythms of production, but beneath the surface lies a complex web of systems, processes, and equipment that must work in harmony to achieve operational excellence. In my years of working with organizations, I've seen firsthand the devastating consequences of reliability failures. The cost of downtime, the risk to safety, and the erosion of customer trust can be catastrophic. But I've also witnessed the transformative power of effective reliability analysis methods. When applied with rigor and discipline, these approaches can unlock the full potential of an organization, driving growth, innovation, and profitability. So, what are these reliability analysis methods, and how do they differ from one another? Let me take you on a journey through the tools and techniques that have shaped my understanding of operational excellence. First, there's the venerable failure modes and effects analysis, FMEA. This stalwart of reliability engineering is rooted in the idea that by identifying and mitigating potential failure modes, organizations can reduce the risk of system failure. I recall working with a leading automaker, where we applied FMEA to a critical assembly line process. By systematically evaluating potential failures and ranking them by severity, we were able to prioritize improvements and implement targeted countermeasures. The result? A 30% reduction in downtime and a corresponding increase in productivity. Next, there's reliability-centered maintenance, RCM. This approach focuses on identifying and addressing the root causes of equipment failures, rather than simply treating the symptoms. I remember working with a major aerospace manufacturer, where we applied RCM to a fleet of high-performance aircraft engines. By analyzing the underlying mechanisms of failure, we were able to develop targeted maintenance strategies that extended the life of the engines and reduced maintenance costs by 25%. Another approach is the Weibull analysis, which uses statistical models to analyze the distribution of failure times. This allows organizations to identify patterns and trends in equipment failure and optimize maintenance schedules accordingly. I worked with a leading energy provider, where we applied Weibull analysis to a fleet of wind turbines. By identifying the underlying distribution of failure times, we were able to optimize maintenance schedules and reduce downtime by 20%. Then there's the Six Sigma methodology, which uses statistical tools and techniques to drive process improvement. I recall working with a leading pharmaceutical company, where we applied Six Sigma to a critical manufacturing process. By identifying and addressing the root causes of variation, we were able to reduce defects by 90% and increase productivity by 15%. Finally, there's the humble Pareto analysis, which helps organizations identify and prioritize the most critical reliability issues. I remember working with a leading retailer, where we applied Pareto analysis to a fleet of distribution center conveyor systems. By identifying the top 20% of reliability issues that accounted for 80% of downtime, we were able to focus on targeted improvements that reduced downtime by 40%. As I look back on these experiences, I'm reminded of the importance of understanding the underlying principles and applications of each reliability analysis method. By selecting the right approach for the task at hand, organizations can drive real improvements in dependability and performance. But there's another lesson I've learned along the way: the importance of human judgment and moral clarity. When faced with complex reliability issues, it's easy to get lost in the data and the analytics. But ultimately, it's the human element that drives decision-making and shapes the outcome. It's the ability to prioritize, to trade off competing interests, and to make tough decisions that ultimately determines the success of a reliability program. As I walk through the factory floor, I'm reminded of the countless decisions that have shaped this organization's journey towards operational excellence. It's the collective wisdom of the team, the commitment to rigor and discipline, and the willingness to challenge assumptions that have driven this organization to achieve greatness. In the end, reliability analysis methods are merely tools, powerful tools to be sure, but tools nonetheless. It's the human element that brings them to life, that breathes meaning and purpose into the data and the analytics. And it's this delicate interplay between human judgment and technical expertise that ultimately determines the success of an organization's reliability program.